The last thing I'd like to talk about is different types of electrons. I know that throughout the course I've already mentioned sometimes the word valence electron. We did that, for example, when we were calculating formal charge in some of the molecules that I've drawn out. Electrons can be divided into two types, core electrons and valence electrons. The core electrons are those tightly bound inner electrons that are at the lower energy level that are not involved in chemical reactions. The valence electrons are the outermost electrons. Those are the ones I've been considering when we talked about properties like ionization energy. It's those outermost valence electrons that are involved in chemical bonding, and it's the outermost valence electrons that leave the atom if it becomes a cation. So for example, if I had a sodium atom, I can write the electron configuration using the noble gas core abbreviation. And the core electrons are summarized with just this symbol for neon in brackets. There are 10 electrons in neon, and those are all core electrons of sodium. Sodium has one valence electron, which is in a 3s orbital. That's the electron that leaves the sodium when the neutral sodium becomes sodium cation. Valence electrons are very easy to count for the main group elements. For the main group elements, the valence electrons are the highest energy s electrons and all electrons in partially filled sublevels. So for example, a sodium atom, which we just looked at, has one valence electron, and that valence electron is in the 3s orbital. It doesn't matter which period the element's in. If it's in one of the main groups, so we're not counting the transition metals or the intertransition metals, we can look at the group number to determine how many valence electrons are present. So here I have some old numbering of the group numbers. Remember, now we use just numbers from 1 to 18. If we did that, we'd have 1 and 2 for the first two columns. Then we would skip the transition metals, which is 10 columns worth, and we end up with 13, 14, 15, 16, and 17 for these group numbers. And over here at 18, we would have the noble gases. So you can pick any of the main group elements and determine how many valence electrons it has. For example, 10. 10 is in group 14, so it has 4 valence electrons. How about selenium? Here's one for you to try. How many valence electrons does selenium have? Thank you for answering. If you look on the periodic table, you see that selenium is in group 16, which means selenium has 6 valence electrons. The issue gets slightly more complicated for transition metals. In transition metals, the outermost or highest energy s electrons are still considered to be valence electrons because we do observe reactions where the s electrons are involved. And usually we count all of the outermost d electrons. Now if we went back to the previous slide, we were not counting any electrons that are in the d sublevel. We were not counting those as valence electrons for the main group elements, were we? For the main group elements, we were considering the d electrons as part of the core electron set. But in the transition metals, sometimes the d electrons are very reactive. So for example, for nickel, if we were going to ask how many valence electrons does nickel have, the answer would be 10 because there's 2 electrons in the highest energy s orbital and there are 8 electrons in those high energy d orbitals. Copper does something a little bit strange. The transition metals, it turns out, likes to have their d sublevel either half filled or fully filled. So sometimes the transition metals will promote 1 or even 2 of the s electrons into the d sublevel so that the d sublevel is half filled or fully filled. Remember, when N gets high, when N gets up to 4, 5, and 6, the energy levels are very, very close together anyway. Do you remember that from the Bohr model of the hydrogen atom? So it doesn't take much energy to change the electron from one atom to another once we're that far away from the nucleus. So that's what copper does. It promotes one of its s electrons into the d sublevel so that it can have a filled d shell. Zinc would have the full electron configuration given by argon 4s2 3d10. As it turns out, for zinc, The d electrons are not used for bonding. So some people would say that those aren't really valence electrons, but I'm going to say the outermost d sublevel we're going to call valence electrons for all of the transition metals. Let's do some examples. How about cobalt? Well, cobalt's full electron configuration is argon 4s2 3d7. But remember, the electrons that are symbolized by argon in brackets are the core electrons. So its valence electron configuration would be 3s2 3d7. What about for antimony? Well, antimony is a main group element. Remember, for the main group elements, we're going to count the highest energy s electrons as valence electrons, and we're going to count the electrons in any partially filled sublevel as valence electrons. What that means is that the electrons that are symbolized by the krypton in brackets are not valence electrons, and because the d sublevel is filled and this is not a transition metal, we're not going to count those as valence electrons. Those are considered core electrons. So antimony has 5 valence electrons, and its valence electron configuration is 5s2 5p3. What about osmium? So for osmium, find it on the periodic table. You'll see that its full electron configuration is xenon 6s2 4f14. Don't forget about those f orbitals. Sometimes students forget they're there because they're tucked down underneath. 5d6. Well, it's a transition metal, so we're going to count its valence electron configuration as its highest energy s electrons and the electrons in the d sublevel. But the f sublevel is filled, so we're going to count those as core electrons. So the valence electron configuration for osmium is 6s2 5d6. The reason that we're writing the valence electron configurations this way is we're thinking about experimentally what kind of reactions do we see for these elements, and which electrons are involved in those reactions, and those are the ones we want to define as valence electrons. All right, let's come back full circle since we're at the end of the week. We began the week by looking at the Bohr model of the hydrogen atom, didn't we? And doing some observations of atoms and their atomic emission spectra. Let's look at the Bohr model for some different atoms. This would be hydrogen. Helium, of course, would have 1 more proton and 1 more electron, wouldn't it? And we can go across the periodic table to lithium, beryllium, etc. We could keep adding protons and electrons until we get all the way up to sodium. So this is n equals 1. This is n equals 2. This is n equals 3, isn't it? So there's 2 electrons in the 1s sublevel. There's 8 electrons here. Some of them are in the 2s sublevel and some of them are at the 2p sublevel. And there's 1 electron in the 3s sublevel for a sodium atom. Of these 11 electrons, which of these have the lowest energy? Remember, the electrons are negatively charged, so the energy of the electrons are going to increase as we move away from the positively charged nucleus. Please go ahead and try to answer this question now. Which of these electrons have the lowest energy? Thank you for your answer. Hopefully you realize that the 2 electrons which are closest to the nucleus have the lowest energy. And in a sodium atom, the highest energy electron is this 11th one that's in the 3s orbital, and that's the only valence electron for the sodium. This concludes our introduction for electron configurations. Now that we understand how to identify the core and valence electrons in an atom, we're ready to start looking at molecular structure and shape.